Hello everyone, welcome to Mindspan Education. Till now, we have already seen these chapters, function, limits, continuity and differentiability, all these things. Our today's topic is Taylor series, as you can see on the screen. In this lecture, we are going to discuss about Taylor series, expansion of a function, uh, and the magical formula uh, that we use to predict a function based on the knowledge of the derivative of a function at any particular point. Okay, all those things we will discuss in this lecture, and also we will try to get around some examples how we use this Taylor series expansion in our particular GATE course. Okay, so let's start. Till now, what we have studied here is whatever we studied, what they give. Why did we study function, limits, continuity, and differentiability? Why did we study all these topics? Because they give us information about the behavior of the function around any point. Okay, whether the function exists or not, whether the function has input domain range or not around on that point, right? Whether the approximate value of the function exists on that point or not, whether the function has any breakage or continuous on that point, if the function is smooth on that point or not, if whether differentiation of the function exists at that point or not, all those things we get to know about by these topics that we have already covered. But the question might arise that why did we study all these topics? Why do we want to know the behavior of a function at any point? Because if we know the behavior of the function at any point, any general point, then we can construct the function. If all the point we know the behavior, then we can construct the function itself, and we can predict the output of the function at any general point, right? That's what we want to do in machine learning or artificial intelligence, right? We need to fit a function, or you can say curve, which is fit being fit by training data. We have training data based on that discrete points. We try to fit a particular polynomial or any other kind of function and try to generalize that, and based on that we try to find uh, behavior of the function that we have constructed based on the training data. We try to find the output on any general data that we have already not fed into that machine, right? That's what we do in the real life, right? Predict the for any input based on uh, the function that we have constructed using the training data, right? So all those things are done using these concepts that we have already studied. If we don't know the behavior of the function, then we cannot construct it. We cannot talk anything about the function. Okay, that's why we have studied these things. Now, so today's lecture we will talk about Taylor series. So let's start that. Okay. So in this lecture, let me start with a question. Rather than any formula or any theory, let me start with a question. My question is, my question is, can we construct, can we construct let me write this properly. Question is, can we construct or reconstruct a function based on based on or you can say rather using only the local information. What I mean by local information, I will tell you now. So question is, can we construct a function using only the local information that we have for that function? Okay. Now, what does this question means? It means suppose you are given at any point. Suppose you are given all the information at any point that you know fa. Let's take the point x equal to a. Okay. This is the local point. You have first derivative f dash a. You have second derivative f double dash a. You have third derivative and everything. What is derivative? How we calculate? That we have already seen in the differentiability chapter. Okay. So you should go through that chapter before this one. Okay. Then only you will be able to correlate properly. Now, if we have all this derivative information about a function around this local point x equal to a, then can we construct the function? A general case. For general case, can we construct fx? Can we find fx by just this local information? Can we do that? Answer is yes, we can do that. Of course, answer is yes. That's why this lecture exists. Now, can we construct fx? What will be fx? That is the question. So, yes, we can construct. Answer is yes, using Taylor series. Okay, using Taylor series, we can construct the function based on only this information. Only now you can see all the information we have at only x equal to a, x equal to a only, here only. All the derivatives, twists and turns, everything we have at x equal to a only. But based on this, we are going to calculate general you can say formula of the function, right? Isn't it very odd? But it works. Okay. So by this, you can intuitively say that Taylor series, whatever we get by Taylor series, that is, we can say like this: Taylor series, whatever polynomial we get using Taylor series, is approximation of the function. Okay, it's not the exact answer, and not exact function in general. Okay, sometimes we get exact function also. I will tell you. Sometimes error terms goes to zero. When we move towards infinity, the error term becomes zero, exactly zero. In those cases, these approximate series matches exact the value of the function. Okay, but in general, they are approximation of the function. What value we get, they are approximate value of the function, not the exact value. Okay. Now let's talk about how we do that. Okay. So the idea of Taylor series is very simple. We try to fit a polynomial based on the local information. So let's talk about x equal to a. This is the point. Okay, this is a local point. This is hero for our today's discussion. X equal to a is the real hero. Now let's try to fit in worst possible way. Okay, at x equal to a, how we can fit this worst. I'm giving you an example. Let's say if fx is the function, then at x equal to a, what should be the value of fx? Fa, right? It should be fa. Otherwise, uh, it will end even before starting. Okay. So if we say that this is our function, we don't know fx, right? We are trying to calculate this fx. We don't know what is this fx. So we say that let let's assume, let's don't say equal to. Okay, let's say this is uh, approximation. Approximation means like this. Okay. Now let's assume this is our function fa. Fa is our function. Worst possible approximation is that constant function. Now what we will get by this? Try to understand. Okay, I'm going into very detail about Taylor series, how we construct Taylor series and why it works. Now, if our function was like this, let's say if our function was some curvature like this, and this point was x equal to a, then this is if our function was like this originally, and we are approximating in most simple way as f equal to a fa, then what function did we approximate? We approximated that fx is fa, means this constant function, right? This is our fa, this is our fx, approximated function. But our function obviously is this curvature, and this is not a very good approximation. Obviously not a very good approximation, but at x equal to a, they both matches, right? But after beyond x equal to a, if this function was not really a constant function, then they differ very much. I mean, at x equal to b, we have some value here, but the function will still give fa at x equal to b, right? So error term is very high. So what we are giving output, that is going wrong by a very large distance, right? तो क्या कहना चाह रहे हैं हम कि ये फंक्शन जो भी हम ये एफ एक्स जो ब्लैक लाइन है, जो एफ एक्स है, इसको यदि हम सिंपल टर्म में यदि एफ ए से ही अप्रोक्सीमेट कर दें, ज्यादा सिंपल क्या हो सकता है? या तो हम जीरो बोल देते, बेटर इससे भी सिंपल हो सकता था कि हम बोल देते कि ये फंक्शन एफ एक्स इक्वल टू जीरो है, दिमाग ही नहीं लगाते, कुछ सोचते ही नहीं है, और हम बोल देते कि ये फंक्शन एफ एक्स इक्वल टू जीरो है, तो वो भी एक अप्रोक्सीमेशन होता, उसमें भी कुछ एरर टर्म होता। बट उससे बेटर होता है कि हम ये बोल दें कि एफ एक्स इक्वल टू एफ ए है, एफ ए जो भी वैल्यू, क्योंकि एफ ए एफ डे से ये सारे वैल्यूज हमें पता है, वी ऑलरेडी नो ऑल द डेरिवेटिव एंड इंक्लूडिंग द वैल्यू ऑफ द फंक्शन एट एक्स इक्वल टू ए। सो वर्स्ट वर्स्ट जो अप्रोक्सीमेशन होगा हम यहाँ से स्टार्ट करेंगे, और भी ज्यादा वर्स्ट से भी नीचे नहीं जाएंगे, तो एफ ए से स्टार्ट करेंगे। तो उससे क्या होगा? उससे ये होगा कि हमारे ये अप्रोक्सीमेट फंक्शन एफ ए जो है, एफ एक्स इक्वल टू एफ ए जो है, ये अप्रोक्सीमेशन तो दे रहा है, बट ये बहुत ही खराब अप्रोक्सीमेशन है, यहाँ एरर के चांसेस बहुत ज्यादा है, राइट? अब इसको हम ठीक कैसे कर सकते हैं? इसको और बेटर कैसे कर सकते हैं? तो बेटर ये होता कि हम यहाँ पे और मैच, इसको इस पॉइंट पे और भी चीजें मैच करने की कोशिश करें। और भी चीजें क्या हो सकता है इस पॉइंट पे? क्या हमें और पता है? हमें फर्स्ट डेरिवेटिव पता है इस पॉइंट पे, राइट? तो फर्स्ट डेरिवेटिव में हम कैसे मैच करेंगे इसको देखो। हाउ वी विल मैच द फर्स्ट डेरिवेटिव? फर्स्ट डेरिवेटिव मीन्स द स्लोप ऑफ द टेंजेंट, राइट? सो फर्स्ट स्टेप, first approximation was fx equal to fa, which was very bad. Now we are trying to improve this. In second approximation, let's name this approximation. Okay, this approximation is called constant approximation, since we put a constant value for the function. Let me write below constant approximation. Now, second, what we are going to do, we are going to improve this, and that will be called as linear approximation. Now, try to understand what we have actually. We have not to forget that we have FA, F dash A, F double dash A. All the information we already know, okay, about that function as per the uh, as per a starting point. We have this information. We have this information about the function. Okay, fa, f dash a, f double dash a. All this information we already know about that function on this local point x equal to a. Now, if we try to add this f dash a in this function, then what we will get? We are going to get what this f dash a says. First derivative is says the slope of the tangent, right? So in linear approximation, how we are going to write this? Fx will be almost equal to fa plus f dash a, the equation of a straight line, right? Y equal to mx plus c, all these things. So m is the slope of the tangent, which is f dash a. This will be the linear approximation. How it is working? Why did we write it like this? First, try to understand. Why it is x minus a, not x. Okay. When we put x equal to exactly a, then we should still get fa, right? Because those discrete point, we already know the value of the function. So error terms should not be there. Any कोई भी एरर टर्म होना नहीं चाहिए. यदि हम एग्जैक्ट x इक्वल टू ए ही इसमें पुट करें, तो कोई भी एफ ए के अलावा और भी कुछ बचना नहीं चाहिए इसमें. तो जितने भी एफ ए के अलावा जो टर्म है, उनको हम x माइनस ए से मल्टीप्लाई कर रहे हैं, ताकि इसमें हम x इक्वल टू ए रखें तो सारे टर्म वैनिश हो जाएं, जीरो हो जाएं एफ ए के को छोड़ के, ताकि हम एटलीस्ट जो चीज ऑलरेडी पता है वो भी गलत अप्रोक्सीमेट ना करने लगे. ओके, सिंस हमें एफ ए पता है कि x इक्वल टू ए पे वैल्यू एफ ए है, तो वो भी जो चीज पता है कम से कम वो तो गलत ना दे. ऐसा भी खराब अप्रोक्सीमेशन नहीं करना है हमें, राइट? तो लीनियर अप्रोक्सीमेशन को हमने इस तरह से लिखा. fx is almost equal to this may be equal to means approximation. It's not equal to but approximately equal to fa plus f dash a x minus a. ऐसे लिख सकते हैं. अब इसमें क्या होगा, इसका यदि हम ग्राफ बनाने की कोशिश करें तो व्हाट वी आर गोइंग टू गेट, सी. I always face problem in drawing graphs. Now bear with me. So this was our function, right? And this was our point. First approximation was a constant function fa. Next, our next approximation is tangent of this curve at this point. So this is the tangent, right? In one attempt, I draw the tangent properly. That's very nice. This is x equal to a. Now see, now we have little better approximation than the previous one. This is more, this new red line is more closer to the function than the previous constant function, right? This is fx equal to, let's not write those long term again and again. Just write this as actual fx, okay? This actual fx we don't know, okay? Here, why we are drawing this? Because we are trying to understand if this was the function, then how much our approximation is going close to the actual value. That's why we are drawing this black curve all this time, okay? X, and this is y means fx, okay? Now, at this point we are still having y equal to fx equal to fa. That means the first term should match. Even if we have this line, even if we have this line, this still does not fail at exact point fa. Okay, if we put x equal to a, then this will still give me fa plus f dash a plus f dash a into x minus a, right? Now you can see there is an improvement. Okay, we have improved little bit from the previous constant approximation. Improvement is that by seeing at the graph itself, you can find out that this new linear line is closer to the actual fx graph than the previous constant function. Unless this actual function was itself is a constant function, then we would not have gotten this f dash a. F dash a will become 0 and fx will become simply fa. Okay. So this is better approximation than the previous one. How we can improve this further? As we are the student of mathematics, we can interpolate this. If we find two, you can say pattern, we try to exploit that pattern and try to use that for our advantage. So pattern here is we keep adding these the derivative information in the polynomial and try to reduce the error term. What we tried here, what we did here in this linear approximation, we tried to reduce the error, the deviation from the actual graph of the function. The deviation, that deviation is called error. Error means whatever value we supposed to get and what value we are actually getting, that difference is called error term, that error that we got, right? We are trying to reduce that error using the derivative information. Now, if we try to add more derivative in this function as we did in the second step, then what we will get? We are going to get how we name this? Add more, add. Let's call it. Here we added the first derivative, that is slope. Here add curvature. Using this curvature information, we can add more information about twists and turns in the graph, right? Then we will go closer to this actual fx, since they will twist and turn at many points. So we need to add those curvatures. So higher order derivative we need to add. How we add those higher order derivatives? Let's see. Let me write this first, and then I will give you exact reason why we are writing it like this. First approximate this fx almost equal to fa plus this linear approximation, and just let's say we don't know this c2. Okay, we don't know this c2, and this is x minus a higher order term. We are adding twist in the curve. Okay, means turns in the curve where it is turning. Higher order will give you the turns. Okay, now we know that if you do double derivative, then we supposed to get f double dash a, which we already know, equal to, if we do double derivative, what will happen? When we do double derivative, this one will vanish, right? Since in first derivative itself this will vanish, this will go to 0. Let me write this whatever I'm saying. When we do double differentiation, anything which has lesser power than 2 will vanish, right? They will at some step they will become constant term and they will vanish. So what we will left with, if we try to calculate the exact function at that point, then we will have f double dash a equal to, this will vanish, this will also vanish since it has x raised to power 1. So in first derivative this will become constant, in the second derivative this will become 0. So all of these will become 0 and c2 will remain c2, and this 2 will become 2. First time 2 will come out, second time 1 will come out, right? 2 into 1, 2 into 1 into x will become 1, right? X already became 1. This will become like this. Now, if we compare this, then we will get C2 as f double dash a, which we already know, by 2 into 1. This we can write as f double dash a by factorial 2. If we go on doing this, add second term, add third term, add fourth term, then at each time we can say that in general term we can say that what we are going to get. Why we get this C2 as a f double dash a by 2 factorial? Because we are matching the derivative, whatever approximate polynomial we are writing, it should match the derivatives. Since we know the derivative information at x equal to a, so if we do that many times of differentiation of this polynomial, at that point we should match those differential value, right? मेरा कहने का ये मतलब है कि वी ऑलरेडी नो दिस एफ डबल डैश ए, राइट? यदि हमने ये लिखा है फंक्शन का अप्रोक्सीमेट पॉलिनोमियल, तो इसको यदि हम 2 बार डिफरेंशिएट करें तो जो भी वैल्यू जो सी टू को, ये जो कांस्टेंट कोफिशिएंट है, इसको हमें इस तरह से रखना पड़ेगा कि हमें जो भी वैल्यू सी टू का है वो एफ डबल डैश ए वाले से मैच होना चाहिए, राइट? इस तरह से C2 रखना है कि डबल डिफरेंशिएशन करने के बाद यदि हम इसको निकालें, हम इसका एग्जैक्ट वैल्यू एक्स इक्वल टू ए पे, तो ये एफ डबल डैश ए से मैच होना चाहिए, जो कि यहाँ मैंने लिखा, राइट? उस हिसाब से हम यदि कंपेयर करेंगे तो C2 मेरा एफ डबल डैश ए बाय 2 फैक्टोरियल है। उसी तरह से इसको यदि हम जेनरिक टर्म में लिखें, टू मैच all differential at x equal to a, जो कि हमें ऑलरेडी पता है, we will get approximation as, क्या मिलेगा हमें? What we will get? We will get fx equal to fa plus f dash a into x minus a plus f डबल डैश ए। कंपेयर करके आपको मैंने दिखाया कि ये f डबल डैश ए बाय फैक्टोरियल 2 है इन द लास्ट एक्सप्लेनेशन। उसी तरह से ये फिर आगे जाएगा तो f ट्रिपल डैश ए बाय फैक्टोरियल 3 आएगा, x माइनस ए का होल क्यूब आएगा, ऐसे ही इन्फिनिटी तक चलता रहेगा। ये सीरीज हमें मिलेगा। ताकि ऐसा क्यों लिखा हमने, ये पॉलिनोमियल के कोफिशिएंट हमने इस तरह से क्यों लिखा? इसलिए लिखा क्योंकि इसमें यदि हम उतने टाइम्स डिफरेंशिएट करें, जो वैल्यू हमें ऑलरेडी पता है, हमें क्या पता है, फंक्शन का वैल्यू ए पे पता है, सारे डिफरेंशियल ए पे पता है, तो जो जो चीजें हमें ऑलरेडी पता है वो एटलीस्ट ये एग्जैक्टली आउटपुट देना चाहिए, वो अप्रोक्सीमेशन एग्जैक्ट होना चाहिए। तो वो डिफरेंशियल एग्जैक्ट मैच होने के लिए हम इसको यदि थर्ड डिफरेंशियल तक जाएं तो सारे ये टर्म जो है पीछे वाले सारे ये वैनिश हो जाएंगे। थर्ड तक जाएंगे तो ये सारे वैनिश हो जाएंगे और सिर्फ यही टर्म बचेगा। तो ये जब थ्री बार बार पीछे आते जाएगा एक एक करके तो ये फैक्टोरियल थ्री यहाँ पे ऊपर में बनेगा, राइट। जब डिफरेंशियल करेंगे तो ये नीचे वाले से कट जाएंगे सारे, और क्या हमारे पास बचेगा, सिर्फ एफ ट्रिपल डैश ए बचेगा, जो कि वही होना भी चाहिए, राइट। थ्री टाइम्स डिफरेंशियल इसका करें तो हमें क्या मिलना चाहिए फंक्शन में, एफ ट्रिपल डैश ए, जो कि एग्जैक्ट थर्ड डेरिवेटिव फंक्शन का है, जो कि हमें ऑलरेडी पता है। तो वो मैच होता रहे, इसलिए इसके कोफिशिएंट को हमने इस तरह से लिखा है, एफ डबल डैश ए बाय फैक्टोरियल टू, एफ ट्रिपल डैश ए बाय फैक्टोरियल थ्री। उसी तरह से ट्रिपल डैश का मतलब है कि फंक्शन का तीन बार डिफरेंशिएशन करने के बाद ए पे उसका वैल्यू है। ओके, अब इस चीज को नोट किया जाए। ओके, ये बहुत ही इंपॉर्टेंट है। ये जो फॉर्मूला हमें प्राप्त हुआ है, ये जो व्हाट दिस approximation polynomial that we got for this function is called टेलर सीरीज। ये सीरीज इसलिए कि ये एडिशन के फॉर्म में है, यही है हमारा टेलर सीरीज, राइट। कैसे आया ये मैं आपको डिटेल में अभी एक्सप्लेन करके बता रहा था, कैसे आया, क्यों आया, और इसका क्या मीनिंग है। अब ये हो सकता है फाइनल, इसको लिखेंगे कैसे, फाइनल तो यही है, यदि ए इक्वल टू जीरो ले लेंगे तो डायरेक्ट एफ एक्स हमें मिल जाएगा इसमें। और इसको दूसरे टर्म में हाउ वी कैन राइट दिस, वी कैन राइट इट लाइक दिस, एफ एक्स इक्वल टू समेशन के टर्म में इजी रहेगा, एन इक्वल टू जीरो टू इन्फिनिटी एफ एन ए बाय फैक्टोरियल एन इंटू एक्स माइनस ए रेज टू पावर एन। तो ये ऊपर वाला चीज को ही हमने इस तरह से लिखा है, इसको आप एक्सपेंड करोगे सीरीज को तो वो वापस से वही बन जाएगा, राइट। तो फर्स्ट थिंग मैं आपको क्लियर कर देना चाहता हूं दैट दिस इज नॉट एनी मैजिक फॉर्मूला। ओके, नहीं है ये, दिस इज ओनली polynomial that matches all derivatives at x इक्वल टू ए। ओके, ये कोई मैजिक फार्मूला नहीं है, ये बस ये यूनिक पॉलिनोमियल हमने निकाला जो कि सारे डेरिवेटिव एग्जैक्टली मैच करते हैं फंक्शन के एट एक्स इक्वल टू ए, क्योंकि इसी बेसिस पे हमने इसको लिखा है, राइट। तो ये हमारा टेलर पॉलिनोमियल हो गया, या टेलर सीरीज आप बोल दो, जो कि अप्रोक्सीमेशन होता है फंक्शन का। कहीं भी मैं यदि इक्वल टू लिख रहा हूँ दैट मीन्स ये अप्रोक्सीमेशन ही है। ओके, बाय इक्वल टू आई डिड नॉट मीन एग्जैक्ट एनीवेयर। ओके, बाय इक्वल टू आई मीन अप्रोक्सीमेशन। ओके, तो इस तरह से हम लिख सकते हैं टेलर सीरीज कैसे हमको मिला, इसी इसी को टेलर सीरीज बोलते हैं। इस तरह से जब किसी फंक्शन को अप्रोक्सीमेट किया जाता है अराउंड द पॉइंट एक्स इक्वल टू ए, तो जो भी पॉलिनोमियल हमें मिलता है अप्रोक्सीमेशन पॉलिनोमियल, उसे टेलर सीरीज बोलते हैं। ओके, अब आपके अंदर ये आ सकता है, ये क्वेश्चन आ सकता है, रेज हो सकता है क्वेश्चन। क्या रेज हो सकता है कि आप देख रहे हो यहाँ पे क्या हमने लिया, पॉलिनोमियल को हमेशा लेके अप्रोक्सीमेट करने की कोशिश किया फंक्शन को। तो हो सकता है फंक्शन पॉलिनोमियल हो ही नहीं, राइट। क्यों हम पॉलिनोमियल ही क्यों ले रहे हैं, हम क्यों ना ई रेज टू पावर एक्सपोनेंशियल फंक्शन क्यों नहीं ले लिया अप्रोक्सीमेट करने की, या लॉगरिथमिक फंक्शन, या साइन कोसाइन फंक्शन, ट्रिगोनोमेट्रिक फंक्शन क्यों नहीं ले लिया, पॉलिनोमियल ही क्यों लिया। क्वेश्चन ये हो सकता है, व्हाई पॉलिनोमियल एंड नॉट अदर फंक्शंस, राइट। तो इसका क्वेश्चन आंसर ये है, हम पॉलिनोमियल ही क्यों फिट कर रहे हैं, बिकॉज पहला तो इट इज easy to find differences, or you can say derivatives of polynomial। यदि हम कोई ऐसा चीज ले लें जिसको हम कैलकुलेट करने में ही मुझे बहुत ज्यादा प्रॉब्लम हो रहा है, तो फिर वो फॉर्मूला हमारे किसी ज्यादा यूज का नहीं होगा। दूसरा क्या होता है, आपने देखा होगा पॉलिनोमियल फंक्शन जो होते हैं वो वेल बिहेव्ड फंक्शन होते हैं, प्रेडिक्टेबल होता है उसका जो बिहेवियर होता है, इजी टू डिफ्रेंशिएट होता है, डिफरेंट इजी टू फाइंड डेरिवेटिव कह सकते हैं। और दूसरा कंट्रोल बिहेवियर होता है, कंट्रोल्ड बिहेवियर। ओके, कंट्रोल बिहेवियर से क्या मतलब है मेरा, ये जो पॉलिनोमियल होते हैं वो अच्छे फंक्शन होते हैं, दे आर गुड बॉयज ऑफ कैलकुलस। ओके, वो कंटिन्यूस होते हैं, वो डिफरेंशिएबल होते हैं, क्योंकि इन्फिनाइटली डिफरेंशिएट हमें करना है। हम यदि लॉग एक्स ले लिए अप्रोक्सीमेट करने के लिए, या साइन एक्स ले लिए, वो फ्यूचर में चल के कैसा बिहेव करेगा, नहीं करेगा, किस टाइप का करेगा, ऑक्सीलेटरी फंक्शन है, डिफरेंशियल एग्जिस्ट करेगा किसी पॉइंट पे कि नहीं करेगा, तो हमें नहीं पता होता है, राइट। तो हम कह नहीं सकते, इसलिए हम ये सब चीजें नहीं लेते हैं, हम पॉलिनोमियल लेते हैं ताकि हम इंश्योर हो सके कि वो इजीली डिफरेंशिएबल हो, और कंट्रोल बिहेवियर उसका फ्यूचर में भी हमें पता चल सके कि ये बिहेवियर जो होगा इसका इरेटिक नहीं होगा। हायर ऑर्डर डेरिवेटिव, हायर पावर जब हम यूज करेंगे तो उसका बिहेवियर जो हो कंट्रोल्ड हो, और हमें प्रेडिक्टेबल हो, ताकि हम उस पर रिलाई कर सकें, इसलिए पॉलिनोमियल लेते हैं। हो सकता है कि हम लॉगरिथमिक लें या कोई और लें तो वो ज्यादा सटीक हो सके, ज्यादा क्लोजली आपको दे सके पॉलिनोमियल का फंक्शन का अप्रोक्सीमेशन। बट पॉलिनोमियल इजी टू यूज होता है, कन्वीनियंट होता है, और इसका रिटर्न जो होता है, रिवॉर्ड बेटर होता है बाकी सबसे, इन टर्म्स ऑफ एफर्ट। ओके, और दूसरा चीज ये है कि ये काम क्यों करता है, टेलर सीरीज व्हाई इट वर्क्स, ये क्वेश्चन हो सकता है, राइट। ये क्वेश्चन भी हो सकता है, ये टेलर सीरीज काम क्यों करता है, बिकॉज ये इसलिए काम करता है, बिकॉज इट वर्क्स, or rather I should say Taylor series works, Taylor series works because because the derivatives encode all the twist and turn, all the information about that function, encodes local behavior and the series that we use synthesize और सीरीज, सारे जो लोकल बिहेवियर होते हैं वो इनकोडेड होते हैं डेरिवेटिव्स में, कि उस x इक्वल टू ए पे वो फंक्शन कब मुड़ेगा, कब टर्न होगा, कब ट्विस्ट होगा, एवरीथिंग। एंड द सीरीज सिस्टमेटिकली सिस्टेमैटिकली सिस्टमैटिकली builds here all local behaviors. Okay, systematically builds that behavior using powers of x minus a, right? तो कैसे काम करता है, ये क्यों काम करता है? क्योंकि all the derivative information that we have, they have all the twist and turn information encoded around that point x equal to a। ऑल लोकल बिहेवियर जितने भी फंक्शन के हो सकते हैं वो सारे इन्फिनाइटली हम जूम कर रहे हैं, कह सकते हैं कि फंक्शन को इन्फिनाइट टाइम्स जूम करके देख रहे हैं कि इसका बिहेवियर क्या होगा एक्स इक्वल टू ए पे। और ये जो सीरीज होते हैं सिस्टमेटिकली ये बिल्ड करते हैं सारे जेनरिक फॉर्म में, कि वो बिहेवियर कैसे प्रोपोगेट होगा, वो उसको हम कैसे यूज कर सकते हैं ओवरऑल जनरलाइजेशन, फंक्शन को जनरलाइज करने में, राइट? तो ये कहना बिल्कुल भी गलत नहीं होगा कि जो टेलर सीरीज है, टेलर सीरीज जो है, टेलर सीरीज हम कह सकते हैं इक्वल टू जूमिंग into a function infinitely। ओके, हम जूम करते जा रहे हैं, फर्स्ट डेरिवेटिव पे, सेकंड डेरिवेटिव पे इंफॉर्मेशन देखें, थर्ड डेरिवेटिव पे देखें, और जूम करके हम उसका बिहेवियर देखते जा रहे हैं एक्स इक्वल टू ए पे, और बेस्ड ऑन दैट पावर से एक्स माइनस ए के पावर्स को यूज कर करके हम उसको सिस्टमेटिकली बिल्ड कर रहे हैं वो बिहेवियर, जनरल टर्म में वो कैसे फंक्शन बिहेव करेगा, राइट? और आप कह सकते हैं ये जो टेलर सीरीज है वो एग्जैक्ट वैल्यू नहीं देता है हमें हमेशा, वो एक अप्रोक्सीमेशन है। तो जब भी हम लिखते हैं टेलर सीरीज, तो हम फंक्शन जो लिखते हैं, व्हाट एवर वी राइट द फंक्शन एज एफ एक्स इक्वल टू, वी कैन राइट इट लाइक दिस, टेलर सीरीज जो भी है प्लस एरर टर्म, उसको आर एन एक्स से लिखा जाता है, nth लास्ट टर्म को जहां तक जा रहे हैं हम उसको यदि एरर टर्म बोलते हैं तो एरर टर्म होता है। तो ये इस बात पे डिपेंड करता है कि आर एन एक्स जो है दैट शुड टेंड टू जीरो, ओके, एज n tends to infinity, okay, then we say that बहुत ही इन्फिनिटली जूम करें तो एरर एकदम मिनिमाइज हो जाना चाहिए, तब हम कहें कि सीरीज काम कर रहा है। अदरवाइज वो यदि रिड्यूस नहीं हो रहा है तो हम बोलेंगे कि ये जो अप्रोक्सीमेशन है टेलर सीरीज का वो काम नहीं कर रहा है, एंड इट इज नॉट गिविंग अस द इंटेंडेड अप्रोक्सीमेशन ऑफ द फंक्शन, राइट? तो आपको मैं काउंटर एग्जांपल भी दूंगा अभी कि टेलर सीरीज हमेशा काम नहीं करता है। लेट मी गिव यू ए काउंटर एग्जांपल, ये कोई ब्रह्मास्त्र नहीं है, इट विल नॉट ऑलवेज वर्क, ओके। काउंटर एग्जांपल, suppose we have a function like this, fx equal to ओके, ये एक पीस वाइज फंक्शन है जिसमें फर्स्ट डेफिनेशन ऐसा है जहाँ x जीरो नहीं है एंड ये x इक्वल टू जीरो पे जीरो है. नाउ if we analyze this function, what we are going to get at all point at x equal to 0, all the derivatives are is जीरो. आप यदि डेरिवेटिव इसका निकालोगे x इक्वल टू जीरो पे सारे जीरो आएंगे. तो इस हिसाब से यदि हम एफ एक्स निकालने की कोशिश करें तो हम एफ ए बोलेंगे, जो ये खुद भी एफ ए जीरो है, प्लस एफ डैश ए बाय 1 का फैक्टोरियल. इसको नहीं भी लिख सकते हैं, एक्स माइनस ए प्लस एफ डबल डैश ए बाय 2 का फैक्टोरियल इंटू एक्स माइनस ए होल स्क्वायर एंड सो ऑन. सिंस सारे डेरिवेटिव इंक्लूडिंग एफ ए जीरो है तो एफ एक्स हमें क्या मिलेगा, जीरो मिल जाएगा. राइट, सब कुछ जीरो हो जाएगा. एफ ए जीरो है, एफ डैश ए जीरो है, एट जीरो एफ जीरो जीरो है, एफ डैश जीरो जीरो है, एफ डबल डैश जीरो जीरो है, तो हमें ये मिल जाएगा. एज पर टेलर सीरीज वी विल गेट दिस. राइट, बट obviously our function is not fx equal to 0. तो आप देख रहे हो फंक्शन कुछ हो रही है हमारा. आप देखो ये है हमारा फंक्शन, ये है, ये है हमारा फंक्शन. बट when we apply the Taylor series we get function fx equal to as 0, constant function, 0 function. But obviously this is not the 0 function. We have a very well defined function in this piecewise form and Taylor series is failing here. Taylor series is not able to approximate this function. And why it is happening? It is happening because the error term that we get at the end will not go to 0. At when n approaches infinity, this error term will not go to 0. This will inflate and start rising. After some time it will start rising. और ज़्यादा हम इसको डेरिवेटिव ऐड करेंगे तो हम देखेंगे और भी फंक्शन खराब होते जा रहा है, और भी ये अप्रोक्सीमेशन खराब होते जा रहा है, और भी ज़्यादा एरर मिलते जा रहे हैं. ये एरर टर्म को हम प्रेडिक्ट ही नहीं कर पाएंगे प्रॉपरली. तो कहाँ से हम कह सकेंगे कि ये अप्रोक्सीमेशन करेक्ट है कि नहीं है. राइट, दैट्स व्हाई टेलर सीरीज always does not work, but in most of the cases it does work. Okay. So we can say that whatever we saw this counter example, based on that we can say that Taylor series depends on how fast the error vanishes. Means how fast this error is going towards 0. Okay, if it is not going towards 0, if we move infinitely many times, then Taylor series will not be able to approximate the function completely. It will fail. Okay. Now, from gate perspective, whatever we saw here, we saw how we construct Taylor series, why it works, and what is Taylor series, approximation of a function. Right? Those things we saw here. But we need not to, this is for conceptual purpose, so that we understand exactly why Taylor series works, what it is. But from gate perspective, we need not to remember this derivation all the time, because our main purpose is to solve the question using this Taylor series expansion, solve the limit, find the value, okay, and mark the options. So ready-made basis, we don't always use the derivation of the Taylor series. What we do, we need to recognize the pattern whatever for some, you can say, the popular functions. For popular functions, we need to recognize the pattern. Wherever we recognize that pattern, we know that this is for e raised to power x, this is for sin x, all those things. Okay. Now, so some famous function, we'll know what is the Taylor series for some popular famous function. Okay. ओके, कुछ स्टैंडर्ड फंक्शंस की टेलर सीरीज हम जानेंगे, उससे उसी को यूज करेंगे जो भी है। डेरिवेशन भी हमें पता होना चाहिए, जस्ट इन केस वी कुड नॉट फाइंड मैचिंग एनी स्टैंडर्ड फंक्शन, देन वी शुड बी एबल टू calculate that also. First function, let's say e raised to power x. Okay, here if we try to construct the Taylor series, finally we will remember the exact final formula that we get. Okay, but if we expand this using the Taylor series polynomial, then what we will get? Our f dash x equal to e raised to power x equal to f double dash x equal to f triple dash x. This function e raised to power x never changes, right? It will always be e raised to power x. So at x equal to 0, if we expand this at x equal to 0, at x equal to 0, what we will get? F dash 0 equal to f double dash 0 equal to f triple dash 0 equal to, and so on, will all we go to 1, right? Since e raised to power 0 is 1, means 1. So our formula, what will become our formula? E raised to power x equal to fa. Fa is also 1 plus, first let me write the Taylor series itself, f0. We are expanding this around x equal to 0. So f dash 0 into x minus 0 plus f double dash 0 by factorial 2 into x minus 0 raised to power 2 plus f triple dash 0 by factorial 3 into x minus 0 raised to power 3 plus other terms. If we write this properly, this will become 1. This will become again 1 into x. This will become 1 by factorial 2, or better if we write x square by factorial 2 plus x cube by factorial 3, and so on. It will go on like this only, x4 by factorial 4, so on till infinity. And we can say here, this is exact, this is not approximation, this will give you exact match, because if we write the error term, if we try to check where will the error term go, we can write it like x to the power n by factorial n. Okay, this will be the error term. Now if we try to predict this value at when n tends to infinity, so what we will do, limit n tends to infinity. This portion I'm giving you some better understanding. Okay, this is not required, but I'm still giving you why this e raised to power x is exact match, and this gives you exact answer rather than approximation. This because this error term goes to completely 0 when n approaches infinity. What will be the Rnx? This will become limit n tends to infinity x raised to power n by factorial n. Now here, if you remember, recollect the limit calculation technique, this is not about x, this is about n. The function is in n, so x is a constant term here, and above function is a raised to power, you can say a raised to power x, and below function is factorial x. So this function is higher than a raised to power x, so this will dominate, the lower term will dominate, and 1 by infinity will go to 0. This will become 0. That's why this gives exact match. So e raised to power function will be 1 plus x square by factorial 2 and other terms. This approximation for the Taylor series is exact match for in terms of values of this e raised to power x. Okay. Similarly, some other popular functions like I will not define everything like this. I will just give the formula now. Like if you take sin x, some trigonometric function, sin x will be like if you do the derivative and around x equal to 0, you will get the result. So I'm not going to do that. I'm going to write the exact formula now. And other terms. Okay, you will get this Taylor series approximation for sin x. For similarly cos x, you will get x. Sorry, you will get 1 minus x square by factorial 2. How we can calculate this? By doing those derivatives. Okay, plus x4 by factorial 4 minus all those other higher terms. Similarly, for log x, so it is convenient to calculate log 1 plus x. Later we replace and find the log x. Okay, later means in the questions wherever we get log x. For log x, what we get? We get x minus x square by 2, x square by factorial 2 plus x, sorry, not factorial 2, it is just 2. If you calculate the exact derivative, you will get this x3 by 3 minus x4 by 4 plus like this, other terms. All these things we get using those derivative of Taylor series, how we exactly derived. Okay. Similarly, the binomials 1 plus x raised to power n, how we get nx 1 plus nx plus n into n minus 1 by factorial 2 x square plus n into n minus 1 into n minus 2 by factorial 3 into x cube and other higher terms. Okay, that's how we get the Taylor series expansion of this function. And how we use this, I will give you one example so that you should know how we use these whatever we just understood, whatever we studied. Okay, so I will give you an example. Suppose we have a question. Question is like this. This example will give you better picture that how we use those information that we studied till now. Okay, find limit x tends to infinity or x tends to 0 actually. This is our question. Okay, let me take the proper question, then we will solve. E raised to power x minus cos x minus x divided by x squared. This is our function. Okay, if we are asked to calculate this limit, then one possibility is that we apply L'Hospital multiple times and do the differential and calculate the limit. But best possible scenario is that we use the Taylor series expansion. And what will be expansion for e raised to power x? We only need to be concerned about till the x square. Okay, so higher term we will ignore. E raised to power x, we can write 1 plus x square and some higher terms that we need not to be worried about. I will tell you why just now. Okay, and cos x we can write as 1 minus x square by 2 plus higher terms. Okay, higher terms. Now see, if we subtract this cos x from e raised to power x, then 1 will be gone, x will be there, and x square minus, so this is not x square, this is x square by factorial 2, means x square by 2. Okay, this x square by 2, x square by 2 will become x square. So what we will left with, limit x tends to 0, and we will have x, and this x will be subtracted by this, cancelled by this minus x. Finally here minus x we have here, so we also won't see this x in the final expression. So we have 2 into x square by 2 and plus some higher term of x, divided by, let me write this properly, otherwise you will get confused. 2 into x square by 2 plus some higher term, higher x powers, okay, divided by x square. Now what will happen, limit x tends to 0, and this 2 became 1, and this x square is gone. If we divide, then we will have 1 plus some x will go away from these higher terms also, but some of x will remain, right? Since this is higher than x square, so even if we divide by x square, we will have at least one x left. So if we put x equal to 0 here, everything will go to 0 except this one, right? So what we will finally get, we will get 1. So see, if we applied this Taylor series expansion, we immediately got the answer as 1. We need not to struggle a lot with the calculation of differentiation and multiple L hospital rule, applying multiple times L hospital rule. We immediately got the answer as a limit as 1. So that's how we use this, you can say, the Taylor series. Okay, the one of the usability I explained here in terms of our GATE syllabus. That's how we use this, right? So this lecture will become very lengthy if I take few more examples. So I will try to add some question in the practice section for this on this Taylor series topic. And let me tell you, you must do the practice on these Taylor series expansion for calculation of limits, right? So that will give you more clarity about the concept, how we use, why we use. And this lecture, I hope it gave you clarity about the Taylor series concept, that why Taylor series works and what is Taylor series approximation of a function and how it works, right? That's I tried to explain in this lecture, and I hope I did the justice with this topic. Okay, so we'll try to cover examples probably in the next lecture, and we'll come with future topics in the next lecture. Okay, so till then, happy learning, keep practicing. Thank you, everyone.